AP Chemistry, this is Unit 13 Thermodynamics review of the problems. You've had for some time in there videos talking about this unit, which includes both Unit 5 and this unit, Unit 13. We're putting those together, and we're going to review Unit 5 as part of this lesson. What you should do before doing this is watch the videos, the instructional videos, and then come and do these problems. Now, there's quite a few problems in this problem set. I'm not going to do them all. I'm going to do about 25 of them, and that's going to average about. I've broken this up into 4 lessons, or 4 parts, and it's going to average about 7 problems per part or so. Okay, so do what you can do. You have a lot of other commitments, other classes right now, but the idea is to get you some review. We still have over a month before the AP exam. We're taking it on June the 10th, and keep that date in mind. And I'll be in touch with all of you to give you the logistics, how that's going to work as far as taking this exam. So let's go ahead and get started on this. And these problems are cut and paste either from your textbook or from other books and other sources of AP Chemistry problems. Okay, so 5.2, consider the accompanying energy diagram. Does the diagram represent an increase or decrease in internal energy of the system? So you're starting with reactants energy down here. You're ending up with products up there. The vertical axis represents internal energy. So A would be an increase in internal energy. B, what sign is given to the delta E for this process? Okay, so B is whenever anything goes in, whether it's work or energy. So delta E is change in energy, and that consists of 2 things. Q, which is heat. So this is a review of Unit 5. These are all Unit 5 questions that we have done. And W, which is work. So heat is kind of obvious. Heat going into the system is, if you have a container with a chemical reaction, if heat goes in, that's a positive Q. The one that's not quite as obvious is work. And that's if you take a piston or something that moves and push down against the system, that would be a positive work. But here you're increasing the internal energy. So that's a positive, okay, so when anything goes into the system, that's a positive, so that would be a positive delta E, a positive change in energy. There's more energy in the system at the end of the reaction than there is at the beginning of the reaction. So plus delta E. And C, if there's no work associated with this process, is it exothermic or endothermic? But there's no work, so that means that if this is 0 in this equation, then this has to be positive. Positive Q will lead to positive E. In other words, heat had to go into the system. So that's called endothermic. Remember that term. Endothermic is heat in, exothermic is heat out. Okay, so that takes care of 5.2. Now 5.4, I'm not going to do that on the video, but that's one that we can do together if you come to tutoring, and I'll have the tutoring hours, and they'll be pretty extensive for this last month before the exam. Okay? All right, so 5.5, we'll go on down here. Okay, in the cylinder diagram below, a chemical process occurs at constant temperature and pressure. So it's a little difficult to see from this copy what's happening. This is a piston, and it's pushing down into this cylinder here. So it goes from a volume of 4 to a volume of 2. So the volume has definitely decreased. So is the sign in W indicated by this change positive or negative? Well, the way you can simply say is that this is an example of work being done on the system. Not the system doing work and pushing the piston up, but somebody or something pushing that piston down. That's work being done on the system, down against the system, and that's considered to be positive work. So either if heat goes into this area right here, or work pushes down on it, that's considered to be positive work. So A is going to be positive W. All right, if the process is endothermic, that means heat is going in, does the internal energy of the system within the cylinder increase or decrease. Again, we have this formula. Delta E, change in energy, equals Q plus W. So we already said that this is positive. If it's endothermic, that means heat is going into the system. It's gaining heat. Again, think of it like money into your bank account. If money goes in, it's positive. If money comes out of your bank account, it's negative. So this is heat going in, so that's positive. So then the question is the change in E going to be positive or negative? So if these two are both positive, then this has to be positive. So the delta E is positive. All right. Okay, problem 11. In what two ways can an object possess energy? This is kind of a review of physics. How do these two ways differ? So you have potential energy and see if you remember the other one from physics. I'll just call it potential E, and you have kinetic energy. That's the energy of something actually moving. Okay, so if here you are and you're standing here and you've got a ball in your hand, okay, while it's in that position you're holding it, it has potential energy. Once you let it start to fall, let it drop it and let it fall to the ground, that changes into kinetic energy. In other words, the potential energy is going to decrease as it falls. The kinetic energy is going to increase as it speeds up. You really don't have to understand much more than that, but that's what they're asking about there. So there's potential energy, there's kinetic energy. All right. Okay, those were the only problems for part 1. Now we're going to go on to part 2, and I just have 2 problems for this. Again, these ones that are not circled we can do in tutoring hours if you wish to come, and we can work on these together. Which will release more heat as it cools from 50 degrees centigrade to 25 degrees centigrade? 1 kilogram of water or 1 kilogram of aluminum, and how do you know? Okay, so for this problem we need a formula that we used which relates heat to temperature. What happens with heat to temperature? Let's review what the difference is between heat and temperature. Temperature is the internal kinetic energy of the molecules inside of a substance. It could be a solid, a liquid, or a gas. Even in solids, the molecules inside, the particles inside, are shaking, they're wiggling. If you heat up an iron bar, it will get hotter, it will feel hotter, and that's because the atoms or molecules inside of it are wiggling harder, they're wiggling faster. Okay, so that's temperature. Heat is the energy transfer between two objects of different temperatures. So if you put a cooler object in touch with a hotter object, then the heat will transfer, as you know, from the hotter object to the cooler object. That flow of energy from one object to another is called heat. So the formula, the relationship between these two, we had this back in Unit 5, is Q, that's heat, equals M, that's mass. C is called the specific heat. It's a function of the substance, what it is. So water has a different specific heat than temperature, plus delta T. Okay, so one thing you would need to know for this problem, and they were actually in a table in the book, is that the specific heat of water equals 4.18 joules per gram centigrade. And the specific heat for aluminum is 0.9 joules per gram centigrade. Or it could be Kelvin. It depends. It could be either centigrade or Kelvin. We'll talk about that if it becomes relevant, okay? All right, so what you can do then is plug it in here. So water, the heat would be, the mass is 1 kilogram, but we have to convert that to grams. So a kilogram is 1,000 grams. So it's going to be 1,000 grams times the specific heat of water, which is what we just said, 4.18 joules per gram centigrade. I'm actually going to change it to Kelvin. I think it should be Kelvin, actually. Okay. All right. So grams cancels with grams, and then you multiply it by the temperature. In this case, the temperature change is negative 25 degrees. Now, it says centigrade. That's why a degree on the centigrade scale is a degree on the Kelvin scale. They're the same thing. So it doesn't matter whether, if you're talking about a temperature change, it's going to be negative 25 whether you call it centigrade or Kelvin. All right. This formula calls it Kelvin. This calls it centigrade. So that's actually a little trick to the problem, is to know that you understand that difference. So I'm going to go ahead and Kelvin cancels with Kelvin. Grams, I already canceled grams with grams. So your final unit of measure is joules, which is what you want. All right. For aluminum, we have Q equals, it's the same thing, a kilogram. So that's 1,000 grams times 4.18 joules per gram Kelvin. It's also minus 25. They're asking about how much heat comes out of each of those with a 25 degree temperature change. The sign is going to be negative because that means heat is coming out. Okay, so you can go ahead and do the calculation on this. And for water, it would be for this one, I'm going to write it up here because there's more room. It would be 104.5 kilojoules for water. And for aluminum down here, it would be, okay, and I made an error copying this, it should be that number, 0.90. Okay, so we now go ahead and multiply that, and we get negative 22.5. And that actually should be a negative because it's a negative sign there. It means Q is negative. Okay, and that's going to be negative 22.5 kilojoules of heat for aluminum. So more heat is released by water, 104, compared to from aluminum, which is 22.5. So the key to this problem is knowing this formula. It's a relationship between heat and temperature. Okay, 524, write an equation that expresses the first law of thermodynamics. Let's just state it first. I'll draw a line here. Energy. Okay, so energy is neither created nor destroyed, but the way we state that is simply the equation that we used earlier, and that is delta E equals heat plus work. That should be delta E equals heat plus work. So delta E equals heat plus work. Put that right there. Okay. Under what conditions will the quantities Q and W be negative? Negative Q is when heat leaves the system. The system is simply where the chemical reaction is taking place. Negative work is work done by the system on the surroundings. Okay, so what this was an example of is this piston here. If I move down here, sorry, I'm off screen. If I move down here, so work done by the system on the surroundings. If you take this piston and it's being pushed up, say the gas is heating up, it's expanding and pushing this piston up, that's negative W. Okay? It's actually what you want a system to do. You want the system to be pushing that piston up, doing work against that piston. That's considered negative W. And if heat is coming out of the system, that's negative Q. Okay. All right, let's keep going. Okay, let's move on to 539. So consider the following reaction which occurs at room temperature and pressure. So two chlorine atoms combine to produce chlorine molecule. Chlorine is a diatomic molecule, so naturally two atoms want to come together to form a single molecule of chlorine. And it says that that process has a delta H. And remember, delta H, change in enthalpy, is just, in our world, it's another way of saying Q, heat. It's just another way of saying heat. There's technically a difference between the two, but it's not one that you need to know or understand. So what it says is delta H is negative 243.4. That means that heat energy is coming out of this reaction. So that means over here, before the reaction takes place, it's at high energy, higher energy, and over here it's at low energy. So in order for it to go from high to low, it must give off heat energy. So it says, which has the higher enthalpy under these conditions? The answer is the chlorine atoms. Generally, in life and in chemistry and in nature, things want to go from higher energy to lower energy. They tend to want to settle in at a lower energy. So at the beginning, the two atoms have a higher energy. Okay, let's move on to 41. All right, so you have a reaction. It's two magnesium atoms plus an oxygen molecule are going to combine to form 2 MgO. And so that's a compound, an ionic compound. You can see that it is exothermic. It's giving off heat. That means it goes from higher energy on this side to lower energy on this side. So A, is the reaction exothermic or endothermic? So the reaction is, and this is a multi-part problem, so I'm going to kind of write all my answers for this one over here. So A, it's exothermic. Heat is coming out. So this applies to this question right here. Everything I'm writing here applies to this question. Okay, B, calculate the amount of heat transferred when 2.4 grams of magnesium reacts at constant pressure. Okay, so you got to do a little stoichiometry. So you come to your periodic table, and you see magnesium has a molar mass of 24.31. Let's remember what molar mass means. It means that 1 mole of these atoms, that's 6.022 times 10 to the 23rd of these atoms, is going to weigh, if you put it on a scale, it's going to weigh 24.31 grams. Okay, so let's write that up here. So we're now on part B. And you always have unit of measure and substance. So moles of magnesium equals and that's grams of magnesium. Okay? So you have grams here of magnesium. You need to convert it to moles. Why? Because chemical equations only understand the language of moles. It's matching up 2 magnesium atoms with 1 oxygen molecule, O2 molecule, to produce 2 molecules of MgO. So it's interested in numbers of particles, numbers of atoms, numbers of molecules. It doesn't care about weight. It doesn't understand 2.4 grams. So why do we use it? Well, because atoms and molecules are too small for us to see. And moles, this could be 2 moles of magnesium plus 1 mole of O2 gives you 2 moles of MgO. A mole is too big for us to count. 6.022 times 10 to the 23rd is too big a number for us to count. So one of them is too small, the other's too big. So we need a way to basically work with this equation, and fortunately we know these relationships between moles of magnesium and how much they weigh. So we know if we have this much, 24.31 grams of magnesium, we know that we have 6.022 times 10 to the 23rd magnesium atoms. All right, so but we're given is 2.4 grams, so let's go ahead and write that. So we're starting with 2.4 grams of magnesium, and what we're trying to get over here is moles of magnesium because that's what the chemical equation understands. So one of these goes on top, one of these goes on the bottom. Remember how we used to draw the boxes like this? Okay, so which one on top, which one on bottom? We need grams of magnesium to cancel out because it doesn't appear in the final answer, but what does is moles. So we need moles on the top, grams on the bottom. So we'll go ahead and write that. Okay, so grams of magnesium cancels with grams of magnesium. The unit that you have left at the end that didn't cancel is moles of magnesium, which is in your final answer. That's how these problems work, okay? So what that means is you're going to end up with, I'll write it down here, there's a little more space, is 2.4 divided by 24.31. And that gives us this, okay, 0.099 moles of magnesium. All right, so what it's saying is that 2 moles of magnesium is going to give off 1,204 kilojoules of heat. So how much will 0.99 moles of magnesium give off? So how do we do this? Well, here's what we do. We say that we see that 2 moles of magnesium is going to produce negative 1,204 kilojoules of energy. So we have a relationship there between moles of magnesium and how much energy it produces. Okay, and I'm just going to write that down here. That 2 moles, again, this number can either represent atoms or it can represent moles. Well, we deal with moles because they're big enough for us to actually see with our eyes and weigh on a scale. So 2 moles of magnesium equals negative 1,204 kilojoules. So but we don't have 2 moles, we have this many moles. So we need to make a conversion. It's basically like setting up a proportion. But here's the way we're going to do it. We're going to say 0.099 moles. And just like we did the stoichiometry up here, we put one on the top, one on the bottom. Which one goes on top? I'm going to draw my box here. And what are we trying to get to? We're trying to get to kilojoules. Some number of kilojoules. In other words, we know that 2 moles produces this many kilojoules. We want to know how many kilojoules this produces. So we take this and we set it up as a ratio. What has to cancel here? You have moles of Mg at the beginning. You want to end up with kilojoules. So we're going to put 2 moles at the bottom and the 1204 kilojoules at the top. So moles of Mg cancels with moles of Mg, and you end up with kilojoules on the top. See, it's the way you set up all these problems like this, all right? So it's 0.99 times 1,204 divided by 2. You multiply everything on the top, and you divide by everything on the bottom. And that gives us 59.6. And it's negative because it's coming out. 59.6 kilojoules. Okay? And that's the answer to that. Okay, so all of this was part B here. Now see, how many grams of MgO are produced during an enthalpy change of negative 96 kilojoules. Okay, so let me go ahead and write C down here. So it says that if you produce 2 moles of magnesium oxide, that will give off 1,204 kilojoules of heat. They're asking, what if how many grams of MgO are produced if it gives off 96 kilojoules of heat. So here's the process here. You have to figure out how many moles negative 96 kilojoules will be. If 2 moles is this many kilojoules, how many moles will negative 96 kilojoules be? And then once you have moles, you convert to grams using the molar mass of MgO. So let's start off. I'm going to draw a line here so we don't get these things confused here. Okay, I'm going to start off and let's figure out the molar mass of MgO. It's 24.31 plus 16. That's going to equal 40.31. Okay, so that means 1 mole, because we're going to need that before the end of the problem. 1 mole magnesium oxide equals 40.31 grams of magnesium oxide. Okay, so we've got that. Now we have to set up an equation, and this is going to take a little space. So let me erase this. It's in the way right now. Okay. So what I'm going to do is, it says we're going to start with, it gives us a number to start with, negative 96 kilojoules. And what it wants to know at the end is grams of magnesium oxide. All right, so first of all, let's look at what we need to do. We need to figure out how many moles, if 2 moles of magnesium oxide gives off this much heat, how many moles is required to give off this much heat, because that's what we were given, that we're giving off that much heat. So we need one conversion to convert from kilojoules to moles of MgO, and then once we have that, it asks us for grams. Way over there, grams. So we then need to convert from moles to grams, and that's what we use our molar mass for. Okay, so what relationship do we know? We know that 2 moles of MgO produces this much heat. Okay, so we're going to go ahead and we're going to write a conversion here. And that's going to be 2 moles of MgO for every negative 1,204 kilojoules of MgO, or just kilojoules is good. So we have kilojoules canceling with kilojoules. Then you need to, so now you know how many moles. This is going to compute to how many moles of MgO you have. Now you have to convert that to grams because they're asking for grams. And there's our molar mass. So moles of MgO is on the top, so we need a second conversion. And it's 1 mole of MgO on the bottom. We need moles of MgO on the bottom because moles of MgO cancels with moles of MgO. And then the mass goes on the top in grams. Okay, so everything cancels except grams of MgO, and that's what you want in your final answer. So this was kind of a challenging, it's kind of a good review of stoichiometry here and how you set up these problems. You got to always start with what are you starting with and what do you want to get to. You're starting with kilojoules, and you need to get to grams of MgO. So you start off by writing the number of kilojoules they gave you to start with, and then what you're trying to find at the end, grams of MgO, and you get the units to line up. So we're going to say 96, I'll put the minus sign on at the end, times 2 times 40.31 divided by everything on the bottom. 1,204 divided by 1. And that equals 6.42. And actually 6.43 when you round it. So it's going to be 6.43 grams of MgO. That's how much will be produced in a reaction that gives off 96 kilojoules. Now I had a negative sign there and 1 there, so those canceled out, so it is a positive number for the final answer, okay? All right, not easy problems, but you practice these. I would practice this one to review your stoichiometry as well as your thermochemistry here, okay? So that's an important one to know. Okay, D. How many kilojoules of heat are absorbed when 7.5 grams of MgO is decomposed into MgS and O2 at constant pressure? So they're running the reaction backwards. If when you run the reaction in this direction from Mg plus O2 to MgO, it gives off heat, then in order to go in the opposite direction to break this up into this and this, it has to absorb heat. So that's what they're asking. So it's just to see that you know how to deal with the equation going in the other direction. Okay, so let's set that up. So what number do we start with? How many kilojoules is what they're asking for? So let me draw a line here. Again, we're not going to do another problem until down lower on the page here, so you can use all this space. I would recommend you do these on line paper, though. Okay, so we're trying to find kilojoules. Kilojoules, kJ, okay? So it equals some number of kilojoules. That's where our answer would go. All right. And what are we starting with? We're starting with 7.5 grams of MgO. So 7.5 grams of MgO. Okay, so again, anytime we work with a chemical reaction, we have to, whoops, we're on this one. Anytime we work with a chemical reaction, we have to be in moles. Grams, chemical equation doesn't understand grams. So what are we going to use? We're going to use our molar mass for MgO again. We need to get from grams to moles. Okay, so it's going to be times, hopefully this is starting to come back to you if you haven't done stoichiometry in the last 4 or 5 months. Okay, so it's going to be, I'm going to have to make my boxes kind of small. I don't have a lot of room to work with here. Again, I recommend you do this on lined paper. Okay, so we need grams on the bottom, moles on the top. There's the molar mass, the same one we used before. So it's going to be 40.31. And it's going to be 1 mole. It's 1 mole equals. So grams of MgO, grams of MgO. So now we're in moles of MgO, and we need to get to kilojoules. So we need to see that relationship. And the relationship is the same one we used before. There's 2 moles of MgO for every 1,204 kilojoules. But now we're going in the other direction. So we're going to have to put energy in to break this up, okay? They just threw that little twist into the problem. Instead of going in the forward direction from left to right, you're going in the backward direction. All that does is change the sign on this, okay? You have to put energy in order to break this up. So let's go ahead and do that. So we need moles MgO on the bottom. So now we're dealing with a relationship inside the equation. So it's 2 moles. It's no longer the molar mass, 1 mole equals grams. It's 2 moles equals this many kilojoules. So we're going to have to go ahead and put the 2 moles on the bottom. And the 1,204 kilojoules on the top. And it's positive this time, so because they're moving backwards. Okay, so moles of MgO cancels. The only unit you have left is kilojoules. Okay, for the overall reaction. Okay, so now you're ready to compute, and you get 7.5, multiply everything on the top, times 1 times 1,204, divided by 40.31, divided by 2. And that's going to give you 112 kilojoules. That's how much energy you'd have to put in to break 7.5 grams of this substance into that, okay? Is 112 kilojoules. And that's the answer, okay? It's a positive, by the way, okay? So that's how you do that. Okay, so this was... Okay, 549. So what is the specific heat of liquid water? So that is simply this number. It's one that you almost, when you're doing these problems, end up memorizing. Okay. And it's joules. That's a measure of energy per gram degree centigrade, or, as I said earlier, or maybe I didn't, I don't know, you could say joules per gram degree Kelvin. Okay, either way. All right, so that's the specific heat. So that's unique to water. Water has that. Other substances have different specific heats. Okay, what is the molar heat capacity? So this tells you what the heat capacity per gram is. Okay, notice you have gram there. So what you have to do is convert from grams to moles. So we have 1 mole of water equals, and again you get your periodic table, water is H2O. So 2 hydrogens is 2 times 1.01, that's 2.02, and oxygen is 16. You add those together and you get 18.02 grams. Okay, so don't let all these other units confuse you, the joules and the centigrade and the kelvins. You're just going from grams to moles, so we're going to do this. We'll just go ahead and use this one. There doesn't matter which one you use. And what are we trying to get to? This might not be quite as obvious to see, but it's joules per mole. That's what molar heat capacity is. and the degree centigrade. So the joules and the degree centigrade stay the same, but grams switches to mole. So how do you do that? Well, you need your molar mass. You need the grams on top to cancel. And you need moles on the bottom. So grams cancels with grams, and you have moles of H2O on the bottom, and that would be your answer. So it's 4.8 times 18.02, and that gives us 75.32. Joules per mole. So that's called molar heat capacity. It's the heat capacity per mole rather than per gram. All right. Okay, we're on this problem still. So C, what is the heat capacity of 180 grams of liquid water? Okay. So it's this much per 1 gram. There's 1 gram on the bottom. Whenever you just have a unit of measure and no number in front of it, you can assume there's a 1 in front of it. So 1 gram of water. So they want to know for 180 grams. So this is going to be, let me go ahead and write these, by the way. This was A up here. This one was B here. Let me draw a line between those. That's B. So C is going to be this one. And it's simply going to be 185 grams of water. And this number. So grams of H2O cancels with grams here. And you end up with those two multiplied together. And that equals 773, or we'll call it 774. So what is that? It's what is the heat capacity of 185 grams of liquid water. Okay? And that's going to be joules per degree centigrade. Okay? All right. And finally, how many kilojoules of heat capacity are needed to raise the temperature of 10 kilograms of liquid water from 24 to 0.6 to 42? So you're going to use this formula. Okay, first let's just convert kilograms to grams. So 10 kilograms, there's 1,000 grams per kilogram. So 1,000 grams per 1 kilogram. So kilograms cancels, and you have 1,000 times 10 is 10,000. So they're asking for heat, kilojoules of heat. So we're going to use the formula MC delta T. So mass we just figured is 10,000 grams. C is the number we've been working with this whole time, 4.18 joules per gram centigrade. And then delta T is the difference in these two temperatures, 24.6, 46.2. And that gives us 21.6. Okay, 21.6. Get that out of there. Okay, and that's centigrade. That's the change, so that's this here. In case you don't want to forget where you got that number from. Degrees centigrade is the temperature change there. Okay, and you run the numbers on that, and you get... And you get 903,000 kilojoules. This is in joules, so it's 902,880 joules, but we're going to change that, divide by 1,000, and make it, I'm just going to call it 903 kilojoules. Again, to get from joules to kilojoules, it's 1,000 difference between the two. Okay, that's that. Okay, that wraps up these first two parts. So that was part 1 and part 2, so you kind of could do those at the same time. There's about 8 or 9 problems. Next video, we'll do part 3, the answers to part 3 questions. And so this overall is basically a 3 or 4 day lesson for you to review this week. All right, that takes care of that, and have a good day. We'll see you in the next video, and hopefully see some of you in person at the tutoring hours.